Hello guys, back with another power electronics video, and looking at the picture you can guess that it's another DC-DC converter, a non-isolated one, and just reveal the title. It's the Cuk Converter, and this is different. All the three converters which we have done till date, the buck, the boost and the buck boost, are all second order systems, which means they have one inductor and one capacitor, two storage elements, whereas this is a slightly advanced one. It has four total storage elements, as you can see, two inductors and two capacitors, and that makes this a fourth order converter, which is nice. And yeah, today we are going to be doing this in hardware, and I'm going to explain the schematic as usual. And of course we see the buck, the boost and the buck boost all the time, but the chook is a bit rare. But what makes this converter special is that both the input current and the output current, if you look at the waveforms, they're continuous. That means even during the on and off time of this switch, the current drawn is continuous on both sides, which is good for EMI and all of that. And yeah, it reduces all the noise and all that. So this is a nice converter, and it's a inverting style converter, which means that if you give a positive input, you're going to get a negative output, just like the buck boost. So it's an inverting converter. So basically you can see it's a sort of like a mishmash of our three earlier converters which we have seen. If you see this part, it's exactly like the boost, because there's a input inductor in series with the DC source, and the switch is a low side switch like the boost converter. And if you ignore this part for now, if you see this and this, the load is always between your output and the ground, so that is fine. But if you see this is basically the same LC filter, which is same as our buck converter. So if you see, this input is like the boost, this is like the buck, and the difference is this capacitor here, which is a coupling capacitor. It's a special one. And this diode, if you see, it's a freewheeling diode as always, but the position is different. It's between this node and to the ground. So that's the diode. And what makes this capacitor special and called a coupling capacitor is because it basically transfers the energy from the input to the output, and it's going to get charged both ways. That means when the switch is on, this inductor stores energy, and after this switch turns off, basically it becomes open, this inductor is going to transfer energy to this capacitor. And basically when that happens, this capacitor gets charged with this plate positive, and when the switch again closes, this capacitor is going to discharge in this way basically, and this inductor is going to get charged this way. And in the next cycle it repeats. This inductor is again going to supply to your load, of course, and also going to charge the capacitor in this direction. So basically this capacitor has to be a non-polarized one. So normally whenever we use capacitors for the other three converters, we use electrolytics, because we generally want them in orders of couple of tens of microfarads, like 4700 microfarad or so on. And you don't get that high of a capacitance in non-polarized ones. So this can remain electrolytic, but this has to be non-polarized. Otherwise, if you try to charge an electrolytic capacitor the other way, it's not going to accept it, it's going to blow up. So yeah, you cannot use a electrolytic here. So what I'm going to be using is a polypropylene one, which is a type of material, and it's non-polarized, so we need that. And this inductor and this inductor and another capacitor, right? So this, as I said, can be electrolytic. This inductor and this inductor depends on your choice. I took this to be toroidal, which is better since it has a higher saturation current limit, and the loop is closed in toroidal, so the EMI is also better. So when it's in series with the input source, I found the toroidal to work better. And for this one I used a drum type one, which is a closed core. So yeah, this is smaller than this. The EMI is a bit bad, but it should be fine since it's just for a LC filter. So yeah, these are the components, and of course the load, a resistive one. I have taken a 100 ohm load. So now that we have basically discussed the circuit, let's go to the schematic in Proteus. And yeah, same as our earlier videos, since we're going to be doing open loop, the TL494 as always a great IC. So we have the duty cycle pin set up with a pot to vary our duty from 10% up to 100%. And of course, same as our boost converter, we cannot push 100% duty on this converter because uh, since it's a buck boost type, as I said, up to 50% duty cycle, which means from 0 to 50%, it operates in the buck mode, which means you get a output voltage lesser than your input voltage. And from 50 onwards, it operates in the boost mode, which means you're going to get more output voltage than your input voltage. So if you try and push 100% duty, as you saw in the schema in the circuit here, the inductor is in the input, right? So if you give 100% duty cycle, basically the switch is on for all the time, so you're essentially going to short this inductor, and that's going to destroy the switch and the inductor. So yeah, we can't push 100% duty, but 80% or so should be fine. So yeah, that's the TL494. It's all the standard open collector, oscillator, all of that stuff. If you want more explanation on this, you could watch the earlier videos. So the output of this TL494 goes to the gate driver, the TC4420, which I have used again in the past. It's a nice low side driver. You can't drive high side with this, but since we anyway the switch is low side, which means it's reference to ground. If we see, we can use this, and it's fast. It can supply a lot of current, and the propagation delay is very less, 55 nanosecond, though we're just going to be doing 50 kilohertz, which is not too high. So either ways this should be fine. And the decoupling capacitors and a bypass for that, for the rails. And after that, that's basically our logic circuit to generate the PWM. And this is the power circuit, same as the circuit which I showed earlier. And this is filled in with the values which I'm going to be using. 12 volts input, and as I said, this is toroidal, so I have two 330 microhenries. So if I put them in series, it becomes 660 microhenry. So yeah, that's the input inductor. And that's our switch, the IRFP 260N. It's a 200 volt rated MOSFET. Of course you could go for 100 volt or something, but yeah, this is what I have right now. So yeah, this is the MOSFET, and a series 10 ohm to just limit the ringing and all of that. And this is the coupling capacitor, and as I said, you can see it's 2 microfarad. So uh, I have 1 microfarad polypropylene. So again, if you put two in parallel here two inductors in series, it adds up. Two capacitors in parallel, again capacitance adds up. So 2 microfarad. And the output inductor 1 millihenry, the drum type, and 47 microfarad electrolytic capacitor, the 100 ohm load, and of course the diode. Here I'm not using a Schottky because I have the 1N5819, which is a 40 volt rated one, and that's a bit close. If we maybe push something like 25 volts or so on the MOSFET, the MOSFET basically sees the sum of the input and the output voltages in a Cuk converter. So if you have something like 20 volts, 30 volts on the output and 12 volts on the input, 30 plus 12, it sees 42 volts. So same for the diode, so it's better to use a higher rated one. So I'm using the MER 460, which is a bit of a overkill for this situation. We don't need this 600 volt rated one, but you could use a 100 volt Schottky, that would probably be better. So yeah, that's the entire schematic here. And yeah, we know how the basic operation works now. If you want to learn how exactly the switch states and you know how the equations work out, you could go and check out my earlier video. It's basically a derivation based video. I've shown all the switch states there and even derived the equations. Of course, these values are not chosen randomly, they're designed same depending on how much inductor current ripple and capacitor output voltage ripple you want. So yeah, to actually get those values depending on your input voltage, switching frequency, and all of that, you can just substitute it into the formulas there. So you could go and check out the earlier video, it's all there in that. And yeah, this is the entire schematic. Again, TL494, TC4420 driver, and the power circuit. So now that that is done, let us switch to the breadboard circuit. Yeah, this is the circuit which I have made. And yeah, preferably don't do this on a breadboard like I have, because as always, the parasitic inductances and even the contact resistances, if you see all of these breadboards, basically the contacts, right, metal contacts with springs. So they don't have zero resistance, they do have at least a couple of maybe 60 70 milliohm, and eventually it adds up with the wires. So if you're pushing high currents, and especially since in the boost mode your output voltage is going to be higher, the input current is going to increase, and at the peak, if we push something like 20 volts or so, our input current is going to go above 1 amp, and that's not great for the breadboard. Breadboards are meant to be low power circuits, so lesser than maybe 500 milliamps or so. But just since we're doing it for a short time, it shouldn't be a problem. But yeah, preferably doing this on a perf board or a PCB is the best way, and there you can view the actual efficiency and all of that. But nevertheless, let's just see where all I've placed the components. So we have the TL494 there, and I've grounded all the, as I showed in the schematic, I've grounded all the analog inputs which I'm not using, since this is old IC. It can pick up noise. It's, after all, they are analog inputs, so it's best to ground them if you don't want your output PWM to get affected. So we have that, all of those are grounded, and the RT and CT as calculated for 50 kilohertz, we have it there, 1 nanofarad and 18K, and just another 100 nanofarad on the duty cycle pin, so that just make sure no noise goes in there. And we have the 100K pot there to vary the duty, and the series resistor to make sure that the maximum voltage that the pot gives out is 3.3, since that's what the DTC pin expects on the TL494. So yeah, other than that, we have the open collector output, one of them, since there are two, I'm using one of them, and yeah, a 470 ohm pull up, which should be enough. Can even try 1K or so, but 470 is okay. And yeah, that goes over to the gate driver IC. And since the Cuk converter has a low side switch, we don't need a high side driver. Just a normal driver should be enough, and the TC442 is great for that. It's just a small IC and it should do the work. And it does need decoupling capacitors, so make sure to add them. So 100 nanofarad and 10 microfarad or so bulk capacitor, that should be good. And yeah, just 1K between the TL494's output and the input of the TC4420, just to limit the current and such. So yeah, that is ready, and the output of the TC4420 goes over here to our MOSFET. And yeah, as I said, since the switch in the Cuk converter sees both the sum at its peak, it sees both the sum of the input and output voltage. So if we push something like 20 or 25 volts, the maximum voltage across the switch could go as high as 40 volts or even 45 volts. So the standard IRF Z44N is only a 555 volt rated MOSFET. So with including all the spikes and all of that and all the noise, our MOSFET could get damaged if we use the 55 volt rated one. So preferably use a higher rated one. So that's why I'm using this. This is a 200 volt rated one. But yeah, you don't need such a higher one. But this is the only one which I have lying around right now. So it should be okay. And other than that, as I said, this has two inductors and two capacitors, right? So each of them has to be of a certain type, is what I've noticed, depending on my experimentation. So the input inductor, preferably since it sees the higher input current in boost mode, toroidal is a good choice. So with a higher saturation current limit. So here I have two toroids and they are in series. Each is 330 microhenry. So 660 microhenry in total when you put them in series. So that's my L1, the input inductor. And after that is the coupling capacitor, which is C1, which is the star of the show, which sets this non-isolated DC-DC converter, the Cuk converter, apart from the other three, buck boost and buck boost, because it has this special capacitor which transfers energy between the input and the output, and since it gets discharged and charged both sides, we can't use a electrolytic like how we always use in a boost and buck. So here you need to use a non-polarized one, but since ceramics generally have lower capacitances and this needs to have at least a couple of microfarads to make sure that the voltage ripple is under control, uh, the value which I calculated, I required around 4 microfarad, but currently I don't have 4 of these to put in parallel, so 2 microfarad should be okay. It's just that the ripple would be a bit higher, but that should be fine. So basically this is a polypropylene capacitor, this red one which you see here. They're great for these kind of purposes. So they have, their sway is very less of capacitance and they can generally handle higher ripple current. So each is 1 microfarad, so when you put 2 of them in parallel you get 2 microfarad. So that should be good. That's a coupling capacitor. It goes in series with our inductor, and after that the output side, just like a buck converter, we just need a LC filter. So here we can use a smaller inductor. So here you can see I have the small drum type inductor, it's 1 millihenry, and after that the output capacitor, same as the switch, the output voltage after you boost it, including the spikes and all, the only one which I had was 25 volts. So if we go higher than that, the electrolytic can get damaged, so use a higher rated one. So this is basically 63 volt rated one, so it's a little bigger, but yeah, use a bigger one. So I have this is C2, which is the output. So yeah, that's the whole circuit, and the 9 volt is basically going to power the TL494 and generate the PWM, and the driver and the power stage is powered by 12 volts, which is coming from this supply here. And we're going to be viewing the PWM on the oscilloscope, and of course the output voltage on the multimeter. And as I said, the load is going to be 100 ohm. So of course it's a power resistor, it can't fit in the breadboard. So here I've taken it from the crocodile cables, and yeah, I've kept it here. It's a 100 ohm 10 watt. So yeah, make sure it's a power resistor, otherwise it can burn up. Don't use those small ones. So yeah, that's the whole circuit. Even though it may look like a mess, yeah, just keep the wires spaced apart and make sure nothing gets shorted. As long as you do that, it should be fine. And yeah, I think I forgot to mention this is the diode, which again the leads are a bit bigger. We can't use a standard Schottky here because the 1N5819 is only 40 volt rated. So yeah, for giving some more margin, I'm using the MER 460 here, which is much higher rated. I think even almost 600 volts. So it's a bit of overkill for this situation. So maybe a 100 volt Schottky would be better. But yeah, this is what I have lying around right now. So yeah, that's the diode there. And nevertheless, it's an ultra fast rectifier diode, so it should be good. Since we're doing 50 kilohertz, not too high, but fine. So yeah, that's the entire circuit, and yeah, I'll turn this on and let's see how the converter operates. So yeah, I've turned the circuit on, the battery is connected, the supply is on, and you can see currently we're at minimum duty, which is roughly 10%. That's the minimum that the TL494 can go, and currently we have 0 volts on the output, and that's because I haven't connected the drain of the MOSFET yet. So let's do that and start seeing the output voltage. So yeah, I've connected the output now, and yeah, you can see we're at 2 volts. So let's vary the pot and maybe go higher. So yeah, let's go to say 20%, and yeah, we have 4 volts, and as you can see it's in buck mode right now since 12 volts is a supply voltage. So let's continue increasing this, and yeah, we've reached at 50% duty now, and yeah, we have somewhat close to our supply voltage. And you can see the main thing, which is its output is inverted, it's minus 9 volts, and that's exactly correct for a Cuk converter. So let's go higher, and yeah, now we are at 60% duty and we have started going in the boost region. Our output is 14 volt. So let's continue going higher, maybe 70%, and we have 20 volt, which is great. And let's maybe go 75. Yeah, we have 22 volts, which is awesome, and preferably less than 85%. So maybe we can go 80, that's safe. So we have 25 volts, which is awesome. And yeah, that's, you can see the waveform is starting to get a bit distorted, and that's obviously all these contact resistances and all of them acting up. So let's not stay in this higher voltage region for too long. Let's get that down. And yeah, now we're at about 25%, and again we're back to buck mode. And what I wanted to show you is roughly at 50% duty cycle and adding up the losses, maybe 55 or so. This point, roughly 50%, is your median point where you should get exactly your supply voltage. In that duty cycle, it's neither in buck neither in boost mode. So that's an important point. That's sort of the threshold where it goes over to this, which is the boost when you go above, and here, which is the buck. So that's the interesting point in all of these buck boost converters. So yeah, I'm varying everything using this pot, as I said, and yeah, you can see the output voltage varied. And yeah, we have the load here, and if I touch it, it is getting hot, so you can be sure that the output is receiving the power. And maybe you can even put a multimeter, another here, and monitor the currents, and that way you can even calculate the efficiencies. That's what I'm going to do next. But yeah, maybe in the next video or something I could show that. But yeah, that was the whole point. And minimum, as I said, since it's 10% duty, you can't really get 0 volts in this TL494 setup. If you maybe do it from a microcontroller or something, you can get 0% duty cycle, then you'll get 0 volts roughly there. But yeah, that was the entire Cuk converter. And let me just remove this wire here. And yeah, we're back to 0 volts since the circuit is disconnected. So yeah, that was the whole Cuk converter demonstration.